So let's get started. We'll pick up where we left off last week with power analysis. We kind of wrapped up I think it's chapter 9, incidental materials, kind of got a variety of different loose ends, it kind of feel to it for multiple regression. I know we jumped to structural path analysis first, but that again is in part because I think that for a course that's going to end where we are, that's still within the regression realm. So I wanted to make sure we covered that. The kind of a final topic that they touch on, though I'm not, as much as I like this book, I'm not satisfied with their cover, how they cover power analysis. It's kind of like giving it some recognition that this is something you should think about, some point and click sort of, kind of at a point and click level if you're using some software, but doesn't really get into the conceptual issues of power analysis, which are important if you're if you're actually ever going to do a power analysis or try to interpret one, or even try to interpret one that someone else has done for you. I mean, I've seen all too many times in life where someone has done a power analysis and it's just they've downloaded some software, they're running it off of a website, and they're interpreting numbers that pop up on the screen and plugging them in, and it's like, there's no way that is correct. I mean, I'm looking at it, there's no way you can have a sample of 20 kids with a small effect size and you've got power, adequate power. There's just, you don't understand the concept behind it, and you're looking at numbers, and that's the problem when you've got a screen full of numbers, is understanding what all those different numbers mean. So I'm going to focus on today kind of at a conceptual level of what power analysis is doing from a more simple sort of model, though these principles apply across the board. I mean, this is really what power analysis is getting at, from as simple a model as you can do. That I think helps make it more clear. And to do that, we're going to look at power analysis not from our multiple regression. I think that's part of the problem. They jump in at a level that's harder to understand, to introduce you to power analysis with. We're going to start with about as simple a test. One of this, not quite the simplest test, but a fairly straightforward test with a one sample Z-test. If you go way back to 573, it probably was covered in 573 depending on who taught it, or some equivalent intro stats course. But again, the idea applies regardless. And the one sample Z-test is just a kind of like a t-test where you've got the kind of the key is some parameters, the population variance, so you're able to do a Z-test instead of the t-test. And you only have one sample, and you're comparing you've got one sample, and you're comparing the average for that sample to some specified value that you want to compare. I think kids in my intervention compared to this, it's often like the population average or some other number that you want to compare it to. We'll see in a minute where that's coming from. The idea with power analysis is it's the probability power. Well, it gives you what your power of any design is. You want to do a power analysis before you do your thesis, before you do your dissertation. It's required pretty much all the time before you do a grant. Grants generally want a power analysis because they don't want to give you $1 million and you have an impossible situation, which we've seen. A colleague of ours, he was my mentor when I was an assistant professor, was thrown money by a state legislature to do something, to do a little study. And when he did the analysis, there was no power. It was impossible. There was like zero power. It was impossible to answer the question they wanted. So the power analysis you want to do before the study, because it tells you, in a way, the simplest way you can think of it, it tells you, are you wasting your time? It answers the question of, if the alternative hypothesis is true, if what you think is going to happen is really going to happen, what's the chance you're going to be able to reject the null? what's the chance you're going to know it? If I'm doing an intervention, and my intervention really does work, really does help kids read better, what's the chance that the data will allow me to reject the null hypothesis and conclude that the intervention works? You don't want to do an intervention and you can't conclude that it works, especially if you're right.
Do you need data to do power analysis?
Not necessarily. You often will do. You can use you need estimates. You need to estimate how big of an effect do you think you're going to see, and how big of a sample do you think you're going to have. Those are kind of key numbers. But the estimating how big of an effect you're going to see is probably the biggest challenge and the biggest curse or seduction, depending on how you want to do it, how people manipulate that. So so having some data, doing a pilot study, people will often do a pilot study. And you get a small little sample and you're able to and you're saying, this is too small to find any significant effect, but I want to get a sense of how big of a difference I might see. So often some data will strengthen if you're doing a grant proposal or a dissertation proposal. It'll kind of help if you want to be confident that you're going to find something. But you don't need data. It's all kind of based on the math. So as I said, we're going to do a one sample z-test for simplicity. And to kind of keep it even more simple, we're going to assume we're looking at scores, kids' scores on some reading test that are based on z-scores. So their outcome are, it's a mean of 0 and values, with a standard deviation of 1. So their outcome are z-scores on some standardized measure. And I want to look at some new reading curriculum to see if kids getting this new curriculum perform higher than the average for the population. So I'm working with some kids. You can see it's one sample. There's some, it's more of a limited design, but I know on this there's this instrument looking at reading ability. The average is 0. The standard deviation is 1. And I'm going to give a reading program to a subset, to some kids, and see if their scores are better than that average of 0, on our reading assessment. So there's ways you can, if you're doing a power analysis, there's different types of questions or ways that people approach it. One is that you can say, okay, I want to estimate how big my sample size needs to be to do this study. We've talked about how the standard error gets smaller as your sample size gets bigger. It makes it easier when you're doing your statistical test when the standard error for your regression coefficient or whatever gets smaller and smaller. And that's driven by your sample size. So one question is looking at how big of a sample size do I need? And that's a question, you might see that worded is similar to, if I want my power to be equal to 0.80. And what I mean by when I say my power to be equal to 0.80, what I mean is if the alternative hypothesis is true. So now notice we've kind of shifted. Up until now, we've always talked about assume the null is true. Power analysis, we say if the alternative hypothesis is true, I want to reject the null 80% of the time. Power of 0.80 means the probability of rejecting the null should be 0.8 or more. So 80% of the time, I want to reject the null if the alternative hypothesis is true. So now we're not worried about type 1 errors, that we never ever, we only want to do 5% of the time. Do I want to say, oh, I've got something when it's fake? With power, it's I'm right, and I want to know it 80% of the time. which again, kind of right there tells you we're more concerned with type 1 errors than type 2 errors. Only 5% of the time we want to make a type 1 error, but we're okay 20% of the time making a type 2 error. Okay, and this is pretty standard for a lot of behavioral research. Power of 0.80 is kind of the run-of-the-mill rule of thumb, whatever power that people want. Though, again, just like all rules of thumb, you don't want to live and die by that number. If you're doing an intervention that's going to cost $20 million, you may want to go into it with more power than 0.80. You don't want to spend that money and you just happen to be that 20% that you don't recognize it. So you may want larger power if it's a big, expensive, demanding study. So you're more confident, if you're right, that you're going to reject the null. If you're wrong, it's not, all the power in the world isn't going to help you. But if you're right, you want to be able to reject the null more often in some cases. Again, if it's a big, expensive study, if it's a high-risk study. You know, you don't want kids taking risks, taking unnecessary risks, unless there's a real good payoff that you're going to see that it helps. If it's, on the other hand, if it's a easy, inexpensive, quick and dirty little intervention, you might be okay with a little lower power just to see how it works. So again, we use 0.8 as a rule of thumb, but don't get too obsessed with that number. Again, that's what people typically think is an adequate or goal for your power analysis. So again, estimating n, if I want my power, so one way people approach power analysis is how big does my sample size need to be? So you say if my power, if I want power of 0.8, and I think my effect size is about 0.2 of one standard deviation. That's how big of a difference I think I'm going to see between, you know, from my effect. How big does my sample size need to be? So notice I've got two numbers. I'm kind of given two numbers and I'm estimating the third. I know the effect size, or I'm assuming the effect size, I'm assuming a level of power, and I'm calculating n. You can kind of spin those around and instead say, okay, let's estimate power. And now I'm saying, if I have a sample of 100, this is a different way of approaching power analysis. If I have a sample of 100 and my effect size is 0.2 standard deviations, how big is my power? So now you know the other two and you're solving for power. So that might be a case of, okay, I'm working in a school, I'm working in this setting, this is how big I can get. This is what my sample size is going to be. Am I going to have adequate power given that sample size? Or you might be estimating the effect size. If I want my, and this question might be framed, if I want my power to be 0.8, and I have a sample size of 100, how small of an effect can I detect and still have power at 0.8? So again, this is kind of, okay, I've designed a study. I do this actually a lot because sometimes I'll typically go into studies, kind of the nature of the work I do, very large n's. And so they'll say, well, we want your power analysis. And we'll, instead of saying, oh, we got plenty of power, I'll kind of say, okay, if we've got 3,000 kids, based on the research we think, because we don't have pilot, based on the research we think these math interventions have an effect size of maybe, well, actually I'm not doing it. I got 3,000 kids, and for power of 0.8, I can go down to detecting an effect size really, really small, which is beyond any smaller than that, who cares? It's a non-important effect size. So again, there are all kind of three different ways you're getting at it. And it all comes down to what's going on. There's your estimate of power, there's your sample size, and there's how big of the effect, how big of an effect size you've got. So for this illustration, we're going to ask, do students in this new reading curriculum score higher on our standardized reading assessment than the overall population average? We're going to assume the sample size is 30. So this is like I'm writing a small grant. I'm going to say, okay, I can get a sample size of 30, and their scores are z-scores. Again, I to hopefully make it a little clearer. And I think my effect size, I think this is a powerful intervention. I think my effect size is going to lead to them performing half a standard deviation above average. So that's my effect size, 1/2 standard deviation above average. Now, thinking back again to 573, where we talked, or whoever you had, talked about probability distributions and sampling distributions of the mean. You can think of it, if the null hypothesis is true, and I sample 30 kids, and let's say the intervention has no effect at all, and if the null is true and it has no effect at all, on average, the score, for this sample of 30 kids, their mean score is going to be 0, because that's the population average is 0. On average. But there's random sampling variation. And so if I sample, let's just again assume the intervention has no effect, and Kavanaugh samples 30 kids, you probably won't get exactly an average of 30 for those 30 kids. I'm sorry, an average of 0 for those 30 kids. It might be a little bit above, might be a little bit below. If Chafen does the study and she samples 30 kids, again, she won't get exactly 0 as her average for those 30 kids. It'll be a little above, a little below. And the sampling distribution of the means, that's what this is. It's just kind of like if we sampled an infinite number of times, samples of 30 kids, and calculated the average for each of those samples and plotted those, this is what it would look like. And again, here's the average for their test scores. We'd expect the average to be right around 0, but there's a fair, the average might be as high as like 0.3 or negative 0.2, and because it's not a huge sample size. So kind of power analysis starts with, okay, let's look at what does it take to, so based on this we can ask ourselves, what does it take to reject the null hypothesis? Because that's kind of central to what power analysis is doing. If the alternative is true, what's the probability I'll reject the null? So how do I decide how to reject the null? I have to look at the null hypothesis distribution, the distribution assuming nothing's going on, and ask myself, how extreme does this score have to be? How extreme does the average for that sample need to be to say it's so unlikely I'm going to reject the null hypothesis? We'd only see it 5% of the time or less, which is one. If I only see it 1 in 100 times, it's so unlikely, it's so uncommon. We reject the null because we conclude that the average probably really isn't 0. It probably is higher. Well, I should have pointed out I'm doing a one-tailed test because we're only looking at higher scores. Again, to keep it simple, we can do the calculations. And again, what this means is I'm looking at this distribution, and if my alpha is 0.05, I only want to reject the null if I get a score somewhere way out here. And based on the distribution, we know we want that area to be 0.05, equal to our alpha level. Beyond this line in the sand, beyond this line, we reject the null because we'd only see it 5% of the time or less if the null is true. Below that score, we're going to fail to reject the null because we'd see it too often if the null is true. We won't get into the math of how do we figure out, but it works out that this average is 0.3. That critical score, this is that critical mean score, the critical score we need for our sample to reject the null. If the sample average is 0.3, If it's more than 0.3, then we're going to reject the null. So this is all based on the null hypothesis. And we know this going into the study before we ever do anything. Is it a little warm in here, or is it just me?
Kind of cold.
Oh gosh, I hope I'm not getting sick. Okay, I'm starting to feel warm. Not a good sign. Anyway, so we need, this critical score is what we need to reject the null from our average. I need a sample average of 0.3 or more in order to reject the null hypothesis. And we can kind of visualize it here. Our region of rejection, kind of we're rejecting the null above 0.3. We fail to reject the null if we get below 0.3. So that's kind of the first part of the power analysis. What's it going to take to reject the null hypothesis? Then we ask ourselves, okay, what about, now I'm going to assume the alternative hypothesis is true. So now I'm going to kind of keep this in memory somewhere. We're going to come back to it in just a minute. But let's draw a different distribution. And this is the distribution if the alternative hypothesis is true.